Hello, thanks for listening in. It's great to have you with us. In this short video, we will work almost exclusively in the rest frame. Our purpose is to show how the radius of the classical electron functions as an antenna capable of radiating high-frequency vacuum waves. Let's begin by reviewing the problem of an LC resonance circuit shown here. An AC power supply connects in series to a capacitor and inductor, producing high-frequency oscillations of the current. This generates changing magnetic fields surrounding the wires, leading to the emission of a small amount of radiation. This qualifies the AC circuit as a radiating antenna. Generally, this is a tiny effect that most people may not be aware of, but it requires the circuit to possess a small radiation resistance in addition to any other ohmic resistance that might be in the circuit. Now suppose we consider a vacuum gauge electron at rest at the origin of a coordinate system. In the vacuum gauge, the classical electron acquires a radius, allowing it to function as a high-frequency emitter of vacuum energy. According to the diagram at right, the point source is an AC power supply propagating field energy to the particle radius. The radius itself becomes a high-frequency antenna having an internal inductance and capacitance, allowing it to emit field energy into the vacuum. Based on this analogy with the LC circuit, we expect our rest frame classical electron to possess an associated radiation resistance. Now let's see if we can write out the physics of our theory using vacuum gauge potentials. To do this, we begin with the vacuum gauge condition, which is a first-order partial differential equation for the potentials. In the rest frame, the vacuum gauge condition simplifies, and we easily solve for the space-like vector field A sub s. Now let's add the norm of our space-like field to the time component and derive the set of light-like vacuum gauge potentials in the rest frame. It's easy to check that this set of potentials still satisfies the vacuum gauge condition. Next, let's add the complex exponential to both the scalar and vector portions of the vacuum gauge potentials. This defines the potentials as spherical waves capable of propagating field energy away from the source. Associated electric and magnetic field vectors may then be determined from differential operations on the potentials. As a final step, let's evaluate the vacuum gauge potentials at the particle radius. In this equation, we have rewritten the potentials in the SI system of units, and we note that both the scalar and vector potentials have become simple oscillators. The importance of the vector potential lies in its ability to determine a vector electric vacuum current. Moreover, this equation also determines the radiation resistance associated with the electron. This resistance is about 30 ohms, while the magnitude of the current, not shown here, is about 34,000 amps. Next, we combine the current and the resistance to determine the voltage V sub R and also a power formula for radiated field energy. The complex electric charge and the magnitude of the complex current can be derived from the vacuum gauge potentials at the radius, and each are related by the familiar differential equation shown on the left. If we compare the scalar current here with the vector current shown previously, this determines a simple expression for the frequency of the radiation. Now let's determine capacitance and inductance at the radius, which both follow from well-known equations in elementary circuit theory. Numerical values for both are extremely small, which seems appropriate for an elementary particle like an electron. With known values for each circuit element and the frequency, the impedance can be calculated. Of course, the reactance vanishes at resonance, so the impedance is simply the radiation resistance. Finally, we note that the inductance and capacitance can be arranged in separate formulas to determine both the frequency and the radiation resistance. Next, we can show that the maximum stored energy in either the capacitive or inductive elements is exactly the mass energy of the electron. This makes perfectly good sense because energy is continuously transferred between the two, so that for any time tau, the total stored energy is always the mass energy of the electron. A quantum theory of radiated vacuum energy follows by regarding it as streams of massless particles. As with all resonant circuits, the frequency of the radiation is simply the resonant frequency of the circuit. Now introduce Planck's constant and write the energy of each emission as h bar times the resonant frequency. To conserve momentum, assume further that this energy is shared among two oppositely traveling particles so that the energy of each particle is 1/2 h bar omega. An important question is this: how many times a second must this amount of energy be emitted to produce inertial vacuum power, which was already been calculated earlier? This frequency is simply the inertial vacuum power divided by a single instance of the energy released. Not surprisingly, this is exactly the Dirac frequency of the quantized electron. To close, it's necessary to show that our theory still works relative to a moving frame. Here we see that the moving frame 4 potentials become skewed in the forward direction, but the radiation resistance is a Lorentz invariant. Moreover, the energies in the inductive and capacitive elements become 4 vectors, which leads to the 4 momentum of the electron. We'll stop here. Thanks again for listening in and have a great day.